Hey there, welcome back to my YouTube channel. You are watching Build AI with Sandeep. Welcome back, you all, to my new YouTube video. And let's continue our learning that we were trying to understand the journey from transformer architecture to the LLMs. And in my previous videos, we discussed that researchers found the transformer architecture was very powerful and they thought that why don't we increase the number of layers, and they picked decoder because it was good in generation. So when they increase the number of layers more than 12, then something bad happens. Training collapsed and the learning stops. The early decoders stopped learning because of vanishing gradient problem. We discussed this vanishing gradient problem in my past videos, and after that I told you that there were three cures to solve the vanishing gradient problem, and the first one is optimizer trap. That we introduced a new optimizer, that is AdamW. You can see on top of my screen that this is the optimizer that helps in solving the vanishing gradient problem. And the second cure, we talked about that introduction of new optimized activation functions. Activation functions basically introduce non-linearity in our deep neural network. So we will talk about in my next video about the activation function. And the third cure was pre-normalization, that the layer normalization was in wrong place in the transformer architecture. We will talk in my future videos about the pre-normalization thing. So now today's topic is AdamW, and in my last video we talked about the optimizers. That we saw there are different types of optimizers available, and we saw that the main job of optimizer is to update weights in our neural network in order to reach the lowest point in loss surface. So basically, if you remember, we compute loss after prediction and then we find the gradient, or just understand this is a loss curve. So our gradient, we compute loss, then we compute gradient with respect to different weights, and this is called gradient. And this gradient tries to reach at this point. This is the lowest point. This is called global minima. Here the loss will be minimum. The loss is minimum. That's why our gradient tries to reach at this point. So, so let me give you a recap about the Adam optimizer, because AdamW is just an improvement of Adam optimizer. So, so let me tell you that Adam was introduced in 2014, and till 2018, Adam was so powerful. Adam was actually so popular. Why Adam was so popular? Because it tracks two things. Adam tracks two things. Two things. Let me tell you those two things. Adam was a combination of momentum plus RMSProp, and that's why the first thing is empty, the momentum part, and the formula of empty is basically beta 1 mt minus 1 plus 1 minus beta 1 gt. So this is called first movement. First movement. And what is the job of this first movement? So it basically tracks the moving average of past gradients. So let me write, it tracks the moving average of past gradients. So this mt minus 1 part is basically doing the moving average of past gradients, and beta 1 is usually zero point 0.9. It means 90% direction, 90% of the past gradient direction, and 10% to the current gradient. So this first movement help our weight update, help our model to do the weight update less noisy, and it gives the direction that in which direction uh, our weight update should happen. Okay, so let's move to the second moment. There is a second moment, that is Vt, beta 2 Vt minus 1 plus 1 minus beta 2 Gt square. And also the Gt is basically gradient. The gradient that I uh, told you here, the gradient is basically derivative of loss with respect to derivative of weights. So this is basically Gt. Now let me tell you one important thing, that you can see here we take square and here we take only Gt, no squaring. Why is it so? This is because in first movement we want direction. We want direction. So let's understand, if this derivative is like plus 2 minus 2 plus 2. So here we need sign. We need plus minus sign, okay, in which direction we need to move right now. But in Vt, in the second movement, this is called second movement. Second movement. Here the second movement only takes care about the steps, about the step size, how big or small step we need to take during the weight update. So that is why we don't need any direction information, that plus minus sign. So this square gives us only the positive value. So that's why the squaring sign is present in the second movement, and here also beta 2 is usually 0.99 here. So Adam take cares two things. The first thing with the help of first movement is direction, and the second thing with the help of VT, second movement, is step size. That how big or small step it need to take. So whenever there is a gradient is wild, when the gradient is wild, GT is wild. Wild means bigger. Then VT is also large. And when GT is calm, then VT also calms. So that's why now let me write the final formula of the weight update, that W new is equal to W old minus learning rate times MT divided by Vt plus epsilon. So this epsilon is basically small term, small error, so that we can avoid division by 0. If somehow Vt is 0, then we don't want to get the error. That's why we are adding a small epsilon, small term, 0.00001, like this, very small term. Okay. So as we all know now that learning rate decide the step size. So in previous optimizers, the same learning rate used for every step. So for every weight update, but this is adaptive. Adam is basically adaptive. Adam full form is adaptive movement estimation. This is the full form of Adam optimizer. So why it is saying, why we are saying adaptive? Because it behaves differently. When the gradient is wild, then the step size, then VT is also bigger, and this is present in denominator. So when denominator is high, then overall term, then W new becomes low, and when it is low, then W new, or we can say instead of saying W new, we can say this whole term, this whole term becomes small, and in this case becomes large. So 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 we are saying Adam optimizer is adaptive because its learning rate is different at each weight update, because VT is divided by learning rate. That's why learning rate is different for each weight update. That's why it is adaptive, and it is smooth because of the movement part. uh, Smooth in the sense like there is no zigzag motion. It is smooth, it is going like this due to the movement part, because it is not changing direction immediately whenever new gradient is in opposite direction, but it uses 90% of the past gradient direction and 10% of the new. So it is smooth, it behaves smooth whenever there is a direction change. So that's why Adam was so powerful. That's why Adam was so powerful. But now, but now there is a but in Adam, and there is a flow. There is a flow in Adam. Obviously, there is a flow. That's why AdamW came into picture. So now let me tell you what was the flow. So before explaining the flow in Adam, I want you to recall one thing from the machine learning, that in every ML or deep learning models, we don't want just to reach at global minima. We don't want just to reach minimum loss. But we want one more thing. We also want generalization. And what does this generalization means? It means our model work better on unseen data. So you must have heard about the overfitting term. Overfitting arises when our model memorized the training data but did not generalize the data. So when the model memorized the training data, then in the testing phase, when we gave our model an unseen data, then our model performed very poorly. So that is why we need a generalized model, that our model generalize the training data, not memorize the data. So for generalization and prevent from the overfitting, we what we do is we were do or we mostly do in every deep networks or deep machine learning model, whether it is or it is deep learning model. So we use regularization, or we can say regularization or weight decay. What it means? Weight decay is basically deep neural networks basically love smaller numbers, but hates larger numbers. So that's why when some weights are becomes very large, due to that overfitting arises. So that's why we do the weight decay or we do the regularization. Both are the same thing, and for that we add in our loss, we add a penalty term. This penalty term. So we add the square of weights and multiply with the regularization parameter, and this is usually zero point 0.1 to 0.01. Okay, so this is what we do when applying regularization in our model. So you can see now that maybe you can uh, connect that what will be the problem happen in this case. So when we add this penalty term to our overall loss, then remember the formula here. So MT and VT. So in MT also we use GT, this GT. So let me write again this MT and GT, that so that you can understand clearly. Beta 1 MT minus 1 plus 1 minus beta 1 GT. So now here this gradient term also have this lambda W2. So when we do the derivative of loss, then again this will become like lambda W. Okay, we can write this, and squaring, just leave it for now. We can also write it like this. So that's why two good cancel out, and this will be the gradient term. This will be our gradient. So in gradient, now we have this term lambda W, and this is for the weight decay. We want that no weight becomes very larger. That's why at every update we want that larger weight shrink slightly. Okay, so for that purpose, VT do also have this beta 2 VT minus 1 plus 1 minus beta 2 GT square, and in our weight update formula, this is learning rate MT VT plus epsilon. So now here in MT we have lambda W term. This is for the weight decay, and our adaptive mechanism. This is our adaptive mechanism, that this lambda W will also divided by this VT term, the second movement, and our weight decay distorted in this case. So the problems are weight decay. So the weight decay is no longer clean. It is contaminated by the adaptive mechanism. It doesn't actually regularize the way you intended. So, like in big models with millions of parameters, this small distortion compounds badly. And Adam trains fast, but it forgets to stay disciplined. The model memorizes training data more than it should. Generalization suffers. So overall, generalization suffers in this case. Now coming to the topic of the today's video, that that is AdamW, the fix. So what exactly AdamW did? So the fix is elegant. Instead of mixing weight decay into the gradient, which then gets adapted, applied directly to the weights after the Adam update. So let me tell you more simply with the equation so that you can understand. So it has the two steps. The first step, we do the normal update. W, this time I wrote W time, W old minus learning rate times MT VT plus epsilon. So we do the normal Adam update, and after that W new is equal to W temp minus learning rate times lambda w. So we do these two steps are separate. We basically the process is called decoupled weight decay. The process is known as decoupled weight decay because we extract the weight decay. We separate both the steps. So it is like if I can give you a practical real life example. So what Adam was trying with regularization is that teaching a student and parallelly taking exam. Okay, so you are teaching student and parallelly you are taking exam, uh, but the student did not learn. So in AdamW, first we teach the student, make him learn, and then we do the weight update. Then we will take exam of that student, that how it is performing. So this is the real life example we can connect with the AdamW, and that is it. Nothing different, nothing complex in AdamW, but it has the massive impact. It had massive impact. Weight decay is no longer touching the adaptive mechanism, the division by Vt, the second movement. It works exactly as intended. So this is it. This is the uh, this is the AdamW optimizer. It basically separates the two processes. And now let me connect this back to the big picture. Why did AdamW unlock deep LLMs? So when you have a model with billions of parameters, if you remember, GPT-2 had 1.5 billion parameters. So the problem is not just speed, it is generalization at scale. With that many parameters, the model can memorize the entire training set. If you let it, that is catastrophic. So this AdamW had huge impact. And most modern foundation models uses this AdamW. After 2017, when AdamW introduced by the University of Tokyo, almost every model start using this AdamW optimizer. And with this AdamW optimizers, we were able to train our deep transformer models. That is the first statement of our today's video. This is the optimizer that made deep LLMs possible. So in summary, AdamW gives you Adam speed and adaptability plus proper regularization through decoupled weight. It trains fast, it stays disciplined. That combination is why deep transformer works. So, all right, let's bring it all home. So, all right, that is the today's topic. And if this was helpful, please do hit like, share with someone learning about LLM, and subscribe. So, we are building this from the ground up, piece by piece. And in my future videos, we will understand about the activation functions and the normalization, pre-normalization fix. And these two cures are left to understand that why deep neural network, why deep transformer models did not working at that time. And after these these three cures will help researchers to train deep transformer based model. So that is it for today. See you in my next video. Thank you for watching. Goodbye.